Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside, Big Ideas Math Integrated Math 2 folk here for section 8.4, Proving Triangle Similarity by Angle. Now you may be aware now what similarity is all about, but as you know, triangles are very special. Heck, we've done triangle congruence proofs in the past, and I don't know how often we're going to be doing proofs here, so to speak, but we are just going to establish that yes, these triangles are similar for this very reason, angle very specifically. We have two more to do in the next section, 8.5, but we'll save them for 8.5. So for here, just all about angle, getting right into triangles are very special in this very reason. If two sets of angles are congruent, then triangles are similar. We'll let the book probably take care of the rest in the lecture section, which is coming up. If you want to find the rest of this PDF, go to the description section down below and you're going to find it there. And then the problem set, which I'm going to go through, only up to, I think, problem number 33, I do believe. You can also check that one out, print that one out, and write it out as you so wish, or just follow along. Find the timestamps of those problems down below if you want to skip past the lecture portion as well. And guys, away we go. We're going to go ahead and take a look at what this is all about. Use the angle similarity theorem and solve real life problems. Of course, some word problems here and there. Similar figures and similarity transformation are used from previously as we jump into this angle bit. So angle similarity theorem is as follows. I kind of stated it before. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Now this is very unique and specific once again to triangles, not to bigger polygons like quadrilaterals and pentagons and things like that, but very specific for triangles. You can see if angle A is congruent to angle D and angle B is congruent to angle E, then those two triangles are similar. Looks like there's a proof to be had. I don't know if that's us to do or if it is part of, oh, looks like they're going to do it right down here. Perfect. Okay, so with all that in mind, I'll just talk, I'm sure they're going to talk about it as well, but I will at the same time. Notice it's called angle and not angle. You don't need to know that the third set of angles are congruent to each other because they will be. Triangle and interior angle sums are always 180 degrees. So if these are the same and if these are the same, then these have to be the same thing to add to that 180. So we don't need to express the third ones. It's implied. And I think that's just an important part to bring about. Now, I did mention the triangle congruent stuff. You've heard of side, side angle, angle, side, and HL. There is no angle, side, and there is no angle, or better yet, there's no angle for them as well. It is true for similarity, though, and here we have it. But it's the basic same concept that we're talking about here. Now, one more thing I want to make mention of. In the last section, we were... I forget which section, it might have been the last one, but in one of the last sections, we were also really focused on talking about in similar figures, corresponding angles are congruent, whereas corresponding side lengths are proportional. Remember that the angles should be congruent in those cases. That does make sense. Okay, let's take a look at their proof that they have for triangle ABC being similar to triangle DEF, and that's the similarity symbol here. If you dilate ABC using a scale factor from center A, then it's going to grow out to some big amount, and then it now looks like this, to the bigger amount, and you have to translate it over apparently, probably. Because the ratio of corresponding lengths of similar polygons equals the scale factor, then dividing these two is the same as dividing those two, therefore these two are going to be the same. AB prime is the same as DE, so those are equal to each other. By the reflexive property of congruence, angle A is congruent to itself. We haven't done a lot of reflexive property before, talking about a shared angle in two different triangles. See this triangle here, and in this triangle here, they both share the angle A. A being a shared part means that it's congruent to itself, but in two different figures, therefore. That's what they're talking about. We've used it for shared sides, but this is a shared angle case here. Okay, so we have a set of congruent sides with the AB prime and DE. A is congruent to itself, and corresponding angles of similar polygons are congruent. So these two correspond. The polygons are similar, therefore they're congruent to each other as well. And because B is also congruent to E by transitive property, B prime should be congruent to E. So these two sets are congruent here, and these two segments are congruent, so these two triangles are congruent by angle, side, angle. So I like what they're doing. They're going about some bit of talking about dilation, using things to prove triangle congruence, and then show that if you can transform triangle ABC into triangle DEF, then that would make them similar. So composition of rigid motions maps that. Therefore, therefore, it is a similarity. Because you can use dilation and that, then they are similar to each other. Okay, so that's just walking through it. Nothing that I really knew to say specifically with that, so I'm glad that they did it for us. So here's how we use the theorem. We're going to determine whether or not these two triangles are similar, basically using angle, if so, and we're going to justify it. So you have two right triangles. The right angles are going to be congruent for sure. They must be corresponding parts. Clearly C isn't congruent to H, but if you find the other angle, such as measure of angle E, which would be 64 degrees if you use, interior angle sum stuff, you find out it is 64 degrees. Therefore, E corresponds with H in that they are congruent. Because E and H are congruent, D and G are congruent, then these two triangles here are similar by the angle similarity theorem. Now, you need to write it in a very specific way. C with K, the two, I guess those must both be 26 then. D with G, the two right angles, and then E with H, the two 64-degree angles. You can choose which way you want to order the first one, but the next one has to still have corresponding parts. And so that works out. Let's do it again. We'll do some more in our own set later. Excuse me, but here are some more sets of kinds of things you're going to have to do yourself. Like parallel lines, we have to talk about corresponding angles that are congruent, alternate interior angles that are congruent. That reflexive property thing will show up again right here. That's a good example. So, never mind. You know what? These are more examples. Okay, so I thought these were ones we have to do ourselves. Normally I skip those here. So let me move myself and say what I just said. 52 degrees for both of these. They are congruent to each other, also corresponding angles if that matters. And angle A is congruent to itself by the reflexive property of congruence. You can see there, reflexive property. Therefore, these two triangles are similar by angle. Right here, you can have two different sets. They have the vertical angles that are congruent here, which they bring up. Boom. And then they talk about a set of alternate interior angles. In this case, they say angle S congruent to angle U. With this transversal and these two parallel lines, angles S and U are alternate interior. Yes, T and R are also alternate interior angles, but you only need two sets of angles, and they had some diversity. They talked about the verticals and the alternate interiors. So also angle similarity, and that's their triangle similarity statement. Here are ones that we're going to wait on and do some later if we want to look at our own problem set in any time frame. Hey, I moved myself for a flag. All right. Real-life problems. Previously, we learned a way to use congruent triangles to find measurements indirectly. Another way to find measurements indirectly is by using similar triangles. Honestly, I don't know what I just read. I'm going to look at the problem and see if I can explain it. A flagpole, this has relevance. A flagpole, right here, casts a shadow that is 50 feet long. So here's a flagpole, here's its shadow, not drawn to scale. At the same time, a woman standing nearby who is 5'4" also casts a shadow that's 40 inches long. How tall is the flagpole to the nearest foot? So the idea, and I guess they're going to say it, but the idea of this kind of problem is both the person and the flag are standing vertically, and they both have a proportional shadow thing because they're based off the same sun, and they are relatively in the same place on Earth. They're basically right there. So we're talking about the same angle of the sun hitting the shadow. So that's what they're saying, probably. You're given the length of the flagpole, height of the woman, and length of the woman's shadow, and all that kind of stuff. I guess, right here. The sun's rays hit the flagpole and woman at the same angle, and also they're both forming right angles because they're perpendicular to the ground. So that's the important part to understand. This is angle. These are similar triangles. We have congruent right angles, and the angle of the sun ray off the top of the flagpole and off the person. So you build a proportion off of that. The only other thing you have to really be careful of on these things are units. Now, they apply units keeping in mind these are both sets of 5'4" inches is 64 inches, so you got to convert that. And then they can stay as feet as long as you're good with that and you understand the answer is going to be feet. So you do some proportion stuff. Looks like here's your 5'4", 64 inches. You cross multiply and solve. You get x equals 80. The flagpole is 80 feet tall. And yes, this is a very nice problem to do something like that with. This is probably what they were talking about here. Find measurements by using similar triangles. Okay, I'm just going to move forward. All right, cool. We're going straight to the problem set from there. Not too bad. Got under 10 minutes. Let's look at the vocabulary and core concept check before we go to the next set. Complete the sentence. If two angles of one triangle are congruent to two angles of another triangle, then the triangles are, well, similar. That's by angle. Writing. Can you assume that corresponding sides and corresponding angles of any two similar triangles are congruent? No. Angles, yes. Angles, yes. Sides, no. Sides are proportional. So can you assume that corresponding sides of any two similar triangles are congruent? Heck no. No for sides. They would be proportional. Yes for angles. I mean, explain. I mean, that's just what similarity is all about, right? That's just the definition. So not for sides, though. Corresponding sides, that is. Okay, so those are those two there. Let's jump into problems 3 through 33. So 31 problems for those. Hopefully it's relatively short, some drill and kill. I know where these could be proof-based, but I think they're going to stay off of that for the most part. I mean, we're doing proofs, but not like 2-column ones, which is what I'm always in favor of. We'll see if there's any set of graphs. I doubt it. That was more for dilations. So guys, without further ado, let's get cooking. Let me get my pen set up. All right, it's looking good. Numbers 3 through 6, and I'll let the drawing of the triangles be on the left side of the screen while I do some stuff on the right side of the screen. In exercises 3 through 6, determine whether the triangles are similar. If they are, write a similarity statement. Explain your reasoning. If they're not, we say the triangles are not similar, right? So here's the thing. We know that angle H is congruent to angle J. Those are two sets of right angles. So that's one set of angles that are similar. We need to find another set are congruent. We need to find another set of angles that are congruent. G is not equal to K as far as angle measurements, but let's find out like the measure of angle F. Now, one thing the book hasn't mentioned, and I do want to mention it here, and I have mentioned it in the past, is that while a triangle's interior angle sum adds to 180, the two non-right angles in a right triangle are complementary. They add to 90 alone. So instead of including the 90, and I think this will make sense to you, the measure of angle F plus that measure of angle G equals 90, because if I did plus 90 equals 180, with the angle H measurement, I would subtract that over. So measure of angle F is going to be 42 degrees when I subtract the 48 over. Measure of angle F is 42 degrees. That's the same as the measure of angle K. Therefore, angle F is congruent to angle K. This is part of my explanation here. So these two triangles are similar. Here's going to be my statement. I'll try and keep them alphabetical for the first part. F, G, H, E, B, C, D, E, F, G, H is similar to, now which one is F congruent to? K. So I'm going to put K first. G must be therefore with L, right? That must be 48 degrees. And then H is with J, like that, by angle similarity. So it's right here and right here that we show that those two sets are congruent to make that happen. Number 4. I have angle S congruent to angle T. Those are both 35-degree angle measurements, and we're going to do the same thing that we did before with the other sets. Q is not congruent to U, but I wonder if R is congruent to U, for example. Now, this time it's not a right triangle, so this time I'm going to have to like add a little more to 180, if that makes sense. So the 85 and the 35. Let's see if we get 65 out from this. Doesn't look like we will, only because this set is ending in a 0. So 120. So measure of angle R is 60 degrees, which is not equal to the measure of angle U. So therefore V is not also going to be Q, right? This is just a case of not similar. And you don't make a similarity statement out of that. Yes, there are sets that are congruent, and yes, there are sets that we wanted to test for proportionality, but if they are not, or not proportionality, for congruence, but if they are not congruent, then they technically don't correspond, even though you aimed for correspondence. So I don't say something like triangle QRS is not similar to triangle, TUV or whatever. You just say not similar. At least that's how I would go about it. Number 5. You have angle L congruent to angle X, both right angles. Notice I'm not really writing that they are, like maybe you want to do that, say given or all right angles are congruent, something like that. I'm just kind of giving you the math. And I think I'm going to notice that these are also not sets that are congruent as well. M is not congruent to W, but let's see if N is congruent to W. Doesn't look like it's going to be. Measure of angle N plus this 40 should be 90. So measure of angle N will be 50 degrees, which is not the same as measure of angle W. As measure of angle W is 55 degrees. Once again, these triangles are not similar, given an angle-angle test that we were going for. We check mark this thing, though. We give like red X's, like Okay. Kind of want green check marks, wouldn't you say? Let's get that going and use that in the future. Okay. Number 6. I'm going to take a guess that these will be similar. Number 6. Angle C is congruent to angle U. Check. Let's look at, angle D and angle T, no. But how about angle E with angle T? So let's see how the measure of angle E holds up. Let's add it with 82 and 25. Set it equal to 180 degrees. That's 107. And if you subtract 107 from both sides, you do get 73 degrees, which is the same as measure of angle T. Therefore, angle E is congruent to angle T. I don't know why I wrote a J. And then that must mean that D is congruent to S, but we're not working that out. Angle T, that also checks out. So my similarity statement by angle can be something like triangle. You know what? There's not really much room there. Triangle CDE is similar to triangle UST by angle. Okay. Moving on. Number 7 through 10. Show that the two triangles are similar. So I probably will copy and paste these ones over because I want to mark them up more. The first set was determine whether they're similar. This time they are similar. Let's show it. More like a proof thing. It probably would make sense to do these as proofs. I'm just going to mark things up and kind of tell you as they are. Okay. Because, see, this will be less about finding different, well, it depends, but these will likely be less about finding different angle measurements and more about using the ones you have. Okay, angle N will be congruent to angle Z because given. This is kind of a two-column proof. And then angle MYN is congruent to angle, and I want to correspond things, XYZ because they're vertical angles. Angle MYN congruent to angle XYZ because they're vertical angles. Therefore, triangle MYN is similar to triangle XYZ by angle similarity. So I kind of did a two-column proof without doing a two-column proof. You know what I mean? I said I wouldn't write it, and I kind of feel I might need to there. See, so I don't know what those angle Y angle measurements are. They literally could be anything. We don't go by the drawing. They could, well, I mean, anything more, less than like 130 or something. But we're just showing that they are congruent, and it would still satisfy the angle set that we have. Okay, this next set has two, and remember, there's more than one way we can answer this kind of stuff. I mean, bottom line is we're going for angle. All three sets of angles should have congruency with one another. But let's go for diversity's sake and talk about things like, because we have parallel lines here, you have a set of, say, corresponding angles that are congruent, like these two right here. And we can say angle Q is congruent to, and I wouldn't want to call this just angle P. I'd want to say something like MPN, angle MPN, because there are corresponding angles. Now, there's another set of corresponding angles here, and I absolutely could use them, but I already used up my corresponding angles. I want to use another set. I want to talk about angle N being congruent to itself. Now, keep in mind what we're saying there is that angle N in triangle LQN is congruent to angle N in triangle MPN. Because it's the same angle, it's a shared angle in both triangles. This is known as the reflexive property of congruence. But this is used for angles. See, we often use, and I've already mentioned this, we often use this for sets of a shared side, congruent segments. But in this case, we're doing it for angles in triangle similarity. So triangle LQN, as far as corresponding parts go, looks like I'm not caring as much about alphabetical order anymore, is similar to triangle MPN by angle similarity. So showing that they're similar, yes indeed. Let's keep moving forward. Number 9. Let's copy it over. Gonna get a little bit of that circle on here. Okay. Looks like we're going to have to use that reflexive property bit again, and it looks like we do have to come up with another angle measurement somewhere. For example, measure of angle U. Now remember, there's a triangle right here with 85, 50, and then this unknown measure of angle U. So let me start with that. Measure of angle U is 180 minus the sum of 85 and 50. So 180 minus 135, which is 45 degrees. So here's angle U. Now we can see that angle, I can't just call it angle X, but angle YXZ is congruent to angle U. Angle YXZ is congruent to angle U. Not necessarily given, right? We had to kind of figure this out with the third angle, so I'm not really providing a reason, but you can tell that, well, definition of congruence. I'll just say definition of congruence. Equal measures, congruent angles. And then angle Y congruent to itself. You know, I could find out angle Z being 50 degrees for the same reason as angle U was, but let's go back to that other kind of thing. Angle Y congruent to itself, shared angle in both triangles, reflexive property. So these two triangles are similar. Now be careful on which parts you correspond. If I started with YXZ, YXZ is similar to triangle Y corresponds in both, but it's not WU because X corresponds with U, so YUW. YUW, this is angle. Of course, all of these are. I think that's the point. Okay, and then number 10. Now keep in mind, actually, next section you're going to learn two other ones. So it's expected that you do those at that time. They probably give you a few angle ones as well. Number 10. Interesting drawing. Let's bring it up. Okay. On number 10, you have given that angle SRV, angle SRV is congruent to angle U. And you have these parallel lines, and you know, these are the kinds of things that this is why it's not exactly a two-column proof. I'm not writing this out, but I got two parallel lines cut by, for example, a transversal, and I want to use this transversal here because I want to use an angle in this triangle and an angle in this triangle and match them up, say they're congruent, using alternate interior angles. So that's angle TRU. TRU in that triangle, true, is congruent to angle SVR in this triangle, as their alternate interior angles when, SVR. Oh my gosh. When lines are parallel, alternate interior angles are congruent. So let's get rid of some of that. I'll keep the, I'll get the angle congruent steps back. Just looked a little messed up. So, triangle TRU is similar to triangle TRU, the unmarked to the double marked to the single marked, unmarked, double marked, single marked, just like I wrote it here, SVR by angle. Okay. They weren't slow problems, but they also took a little bit longer than I expected. Probably because of the way that I wrote it out. And if you have to draw the diagrams, it might take even longer. So use the diagram to copy and complete the statement. Don't mind if I do as far as copying goes. We want to see which sets of triangles are similar, which sets of measures of angles we have, and things like that. Okay. So more than just number 11 to get ready for. Let's see what we got. So it looks a little cluttered. Number 11. Angle or triangle CAG is similar to triangle what? So CAG is right here. It's not about congruence, it's about similarity. So it could be one of these big triangles here as well. What I am noticing, we have a length of 4, a length of 3, and we haven't yet hit the other. We're probably doing an angle thing is what I'm going to bring about. We're probably going to do an angle thing. So I'm not going to talk about the side lengths yet. Here's what I do see. I see vertical angles right here that are congruent to each other. That's one set. I also see, and there are multiple ways you can do this, I also see right angles here, which means perpendicular lines, which means that's also a right angle and that's also a right angle. So right angles are congruent to each other as well. They don't ask me to explain more than that. So triangle CAG should be similar to triangle CEF. Okay. Number 12. Triangle DCF, and I think will be the same reason on this other set. So triangle DCF, here's D, here's C, here's F. And here's another set of vertical angles here and here that are congruent to each other. And the right angles that are congruent to each other as well. So DCF with BCG. Triangle DCF is similar to triangle BCG. I can probably move these up without incident. Number 13. Triangle ACB. Now ACB is this bigger guy here. ACB. You know, there's a lot that at this point, because we have two sets of similar triangles, I don't know how much we have to play on proof of things, but if those two sets of triangles were similar before, then by corresponding parts of similar corresponding angles of similar triangles are congruent, then that must be 53, and this must be 45. And these two are vertical angles, which are congruent. So I think there's enough angle stuff involved here to say that triangle ACB is similar to triangle ECD. So triangle ACB is similar to triangle ECD. Number 14, measure of angle ECF. Where's ECF? ECF. Okay, so here's the thing about ECF. It is this green guy right here, basically, this kind of thing that I marked there. We note that either this is 53 or this 53, what have you, and that's 90. So 53 plus something is 90. That's what we're trying to figure out there, basically. Measure of angle ECF is 90 minus 53, which is 37 degrees. Number 15, measure of angle ECD. So in a 40, so this angle's 45. This one's also going to be 45. It's a 45, 45, 90 degree triangle. 45 plus 45 is 90. Plus 90 is 180. So that's 45. This one we just found out was 37. They want the measure of angle ECD, the whole thing, we have to do 37 plus 45. Measure of angle ECD is 37 plus 45, which is 82 degrees. The last ones are side lengths. Now, this is not so much about angle anymore. Now that we know of the similar triangles that we have, this is now about proportion buildups that we started to do in section 8.3. The length of segment CF, right here, this is an altitude in this triangle that's similar to this triangle here that has another altitude, and this altitude's length is 4. So CF, this altitude, is to 4, the altitude in the smaller triangle, as, what are the side lengths do we know? 3, as 9 is to 3. And yes, this 9 corresponds with this 3 as far as these length portions go. Because the two triangles are a rotation of one another when it comes to similarity. Remember, it is ACB similar to ECF. So this guy is with that guy. 9 over 3 is 3, but I'll go ahead and just cross multiply to solve here. We got 3 times CF as 36, and CF, its length is 12. So this triangle has lengths that are 3 times bigger than this one. I think that now that's kind of established, that we have that there. And then number 17, the length of BC. B to C is right here. I'm going to... Oh, they have... I wanted to use a Pythagorean theorem thing, but I think we're going to go off this 12 root 2 because this will correspond. As long as we're in something regarding proportionality, let's do as many corresponding bits as we can. However, I could have used Pythagorean theorem and found it a different way. So let's go to, once again, corresponding parts here. We know that the 9 to 3 is also, 3 over 1. That's the similarity ratio from the big triangle to the small triangle. 3 is to 1 for big to small, as 12 root 2 is to the length of BC. 12 root 2 is to the length of BC. Okay, so 3 times BC is 12 root 2. Basically, we have to make it 3 times smaller. BC is the length of 4 root 2. And if I use Pythagorean theorem using a version of something else that I could have done, I would have gotten the same answer. So I like that the problem agrees with itself, basically. And then number 18, the length of DE. This is going pretty fast as a section overall. The length of DE, where's DE? Right here. That should correspond to the length of BA here, which is 7. So DE is to 7 as, well, 3 is to 1, right? Once again, the bigger triangle is 3 times, similar triangles is 3 times bigger, so multiply both sides by 7. Multiply both sides by 7. You get DE is 21 units in length. Okay. Number 19. Describe and correct the error in using the angle-angle similarity theorem. Oh, well, okay. Hold on, I want to see what they actually put. Quadrilateral ABCD is good. Okay, so here's the problem. They're not triangles. These are not triangles. The angle-angle similarity theorem does not apply to quadrilaterals, well, or any other polygon, but this is specifically quadrilaterals they're talking about. They need to apply to triangles. Now, why not? Well, one, triangles are very special in this way. For another, we talked about angle-angle referencing that the third angles would have to be congruent for triangles. But again, there's more to it about triangles being very special. Even quadrilaterals, if I knew all four angles were congruent in a quadrilateral, I'm not going to guarantee they're similar either. So I think that's just the big thing. I don't like when they say correct the error, because generally whenever I hear that, what I'm thinking more so is that, like, do the problem in a way to show how to fix it. There is no way to fix it. We can't. So my correction, I'll just say this. My correction, there is no guarantee these triangles are similar. And I think there's a nice stark difference between saying we can't assume triangles are similar, like I just said, and triangles are not similar. If we go back to the early problems, when I was showing, which page was it? When I was showing something like here, angle R's measure was 60 degrees. Angle U's measure was not 60 degrees. It was, I think it was 65. These triangles were absolutely not similar. Corresponding angles, whatever you were testing for corresponding angles, were not congruent. Here, we do have two sets of corresponding angles, and it's possible that D is congruent with H and A is congruent with E, and those would have to correspond because the order in which they arrive. It's possible, and it's possible the triangles are similar. We just don't have enough information. So how about there's no guarantee? There's not enough info to show that these quadrilaterals are similar. You would definitely have to get bigger into sets of corresponding sides being proportional and things like that. I think that's it. Okay, number 20. Describe and correct the error in finding the value of x. So, this is a good one, but this is a great problem. I'm trying to think that we're going to do triangle mid-segment theorem later. I think it's better served for that section. I think it's section 8.6 is all I was going to say. This is a great problem, though. So take a look at what they did. You do have two similar triangles. Let's just say that, with corresponding angles here with parallel lines and reflexive property and things like that, right? The triangles are similar. So corresponding side lengths will be proportional. So let's set up a proportion to solve for x. They do 4 over 6 equals 5 over x. Now, I think we're generally more ingrained with doing something from one triangle to the other, but it's totally allowed to do these parts like this as long as you're doing corresponding parts and the direction flows the same. So you see this directionality like this. You go from small triangle to big triangle, and you wonder what's wrong with doing that. By the way, they cross multiply correctly. They divide correctly. So what's wrong with this answer? What's wrong is the 5. 5 is not corresponding with 4 in the same way that 6 is corresponding with x. Let's do this in a different way. Let's write out what we're looking at in a different way. 4 is, to us, the left side of the small triangle. 5, I'm going to wait on 5. 6 is the bottom side of small triangle. X is the bottom side of large triangle. 5, is 5 the left side of the large triangle? 5 is a segment of the left side of large triangle. It's not the entire left side. So when you do these things, the correspondence idea is proper for bottom side of small, bottom side of large. They are the whole amounts of those sides. The left side of the small triangle is its whole. This is a segment of the left side of the large triangle. The 5, the length of 5 is not corresponding in the large triangle with what the length of 4 is doing in the small triangle. In the same way that the bottom side lengths correspond in both triangles. Now, once again, this applies a lot more to probably section 8.6 when you use something called the, not the mid-segment theorem. I call it side splitter theorem. There's another name, and I don't know why I'm not thinking about what it is. But what you need to do, and I'm spending way longer on this problem than I need to. You probably already understood what you need to do. What you need to do to correct this is you need to not use 5, but 4 plus 5. You need to do the whole part of the small to the whole part of the big, because here's bottom part of the small and bottom part of the big. This would have gone a lot faster if I only said the things out loud, but now that I'm doing it here, I have to kind of say it that way. So you can do 4 over 6 and stuff, that's fine, but you don't do 5 over x, you do 9 over x. Whether you reduce or not, these numbers are small enough, I don't feel I have to, so I'm going to get 4x equals 54, and x equals, I have no idea. I don't know why I don't. 40, 10, 13 and a half. 13.5. So that's the fix. Again, I spent way longer on that problem than I needed to. I think it's something that's going to just be understood. Whoops, I shouldn't have turned that page. I think it's going to make more sense in section 8.6. Okay, I hope that was a good teaching moment. Let's go to number 21. Modeling with mathematics. You can measure the width of the lake using a surveying technique as shown in the diagram. Find the width of the lake Wx, justify your answer. So we're going to work off of some set of similar triangles. I have vertical angles here that are congruent. And then because these lines are parallel, I can do either set of alternate interior angles such as V and Y that are congruent to each other. You could do the other set as well. You have angle, angle, straight up, no matter what you do there. So I'm just letting you know, based on the vertical angles, based on the alternate interior angles, you can say something like triangle VWX is similar to triangle, that looks really weird, VWX is similar to triangle YZX by angle, angle. So let's find the parts that correspond to find the length of WX. The length of WX is to the length of ZX. Oh, let's write ZX. Well, I'll just write it out. It's ZX as the length of large triangle VW is to the length of YZ, which are known marked bits. So let's find that length of WX. WX is to 6 as 104 is to 8. That's something I'd love to reduce, so I'm going to go ahead and give that one a shot. WX, actually let's just multiply both sides by 6 and see where we go from there. But 104 over 8 is 13, I think. 13 and then times 6, and we get 78 meters, and that should be the length of WX. There's not much different that that problem's doing from other problems with proportions, other than we need units in our answer. Number 22, making an argument. You and your cousin, before I even continue with it, our friend hasn't argued with us very much. It's been more of our cousin and our sister and things like that. I think our friend has dropped out of the argument race. I'm not really sure. You and your cousin are trying to determine the height of a telephone pole. Your cousin tells you to stand in the pole's shadow, so the tip of your shadow coincides with the tip of the pole's shadow. So let's say I have a telephone pole. I'm just going to draw something, whatever. So say I have a telephone pole, and here's you. Okay. And there's you. And you're both standing on the ground. And there's a shadow thing, and you're standing like at the tip of that shadow of the pole, like that. That's kind of what they're talking about. We both make right angles with the ground. Okay? Your cousin claims to be able to use the distance between the tips of the shadows and you. The distance between you and the pole. And your height to estimate the height of the telephone pole. Is this possible? Explain. Include a diagram in your answer. So I already drew the diagram. I don't want to call these both H. I'll call it M. I don't know. Okay. I mean, is it possible? Probably. You have similar triangles. Your cousin claims to be able to use the distance between the tips of the shadows and you. Distance between you and the pole. Wait. Your cousin tells you to stand in the pole's shadow, so the tip of your shadow coincides with the tip of the pole's shadow. Your cousin claims to be able to use the distance between the tips of the shadows. I didn't use the tips of the shadows here. The tips of the shadows and you is here. Okay. Let's do that again. Distance between you and the pole, I have as y, and all that. Is it possible? Yeah, see, I can use, yes. If you know the numbers, I could use Pythagorean theorem to find this one, and then that length could find this one. What are we trying to find? Estimate the height of the telephone pole. Yes, because if we have this, and my height, I could use Pythagorean theorem to find this one, which could use similarity to find this one. Yes. Yep. So, yes, using Pythagorean theorem. So, as long as you understand the setup in the diagram, Pythagorean theorem, I can find the distance of my shadow and then create, well, so okay, so first of all, and then and these triangle, and there are similar triangles by angle. I'm just going to say that that's the case. So we can use proportions with my shadow length to the telephone pole shadow length, because what I can do for that is basically whatever my shadow length is. Let's say my shadow length is A. I'm going to be able to do something like M, my height, is to A, my shadow length, as H, the telephone pole, is to the telephone pole shadow length, Y plus A. So I can use my shadow length to the telephone pole shadow length to find, and my height to the telephone pole's height. A proportion. So that would be the setup there. So yes, I can. Okay. Sorry, I had to first make sense of what the problem was asking. Excuse me, I just inhaled air badly. Okay, I think I'll survive. All right. Numbers 23 to 26. In exercises 23 to 26, is it possible for triangle JKL and triangle XYZ to be similar? Explain your reasoning. So letter order matters here. Okay. Measure of angle J equals 71 degrees. Now, what would J correspond with? J would correspond with X. Now, they also say, I'm going to start writing things out based off what they give us. Measure of angle X, excuse me, is also 71 degrees. So far, so good, because those would correspond. They say measure of angle K is 52 degrees. This is in triangle JKL. Measure of angle Z is not related to this one because it's not a corresponding angle. So measure of angle Z is 57 degrees. So is it possible? We'd have to work that last part out. These are triangles. So measure of angle L is something we'd have to find, or measure of angle Y is something we'd have to find. Let's go for measure of angle Y, knowing that, I always want to write a J. Knowing that Z is 57 degrees, so 180 minus 71 plus 57. which is 180 minus 128, which is 52 degrees, which matches with measure of angle K. So, using angle, is it possible for them to be similar? Yes. Triangle JKL, and I didn't find angle L, but it must be 57, is similar to triangle XYZ. I'll get that ready for each problem to write, copy, and paste. So I don't know if I'm writing the information down the best way possible, but finding the parts that match have to be parts that correspond. It must be the corresponding parts. And they might trick us with that, with another set. Number 24. JKL is a right triangle, and measure of angle X plus measure of angle Y equals 50 degrees. The first one was a definite, it's not only possible they're similar, they were similar. This one, you have to ask yourself a little bit more. So angle JKL is a right triangle. They don't tell you in this case which angle is the 90-degree angle. So, I don't know. Measure of angle X plus measure of angle Y is 150 degrees. Yes, as long as... So, is it possible? Yeah. So, yes, as long as angle X or angle Y is a right angle, is congruent with its corresponding angle in the other triangle, and the other angle, the other corresponding angle pair, both measure at 60 degrees. Measure to 60 degrees. Because 90 plus 60 is 150. So as long as those two are good, then we're good. So if X was 90 degrees, then so would J. J would have to be. And then K would have to be 60 degrees as Y is. That would work out. Otherwise, yeah. But they're just saying, is it possible? Yes. Is it absolute? No. There are a lot of ways that that could not be the case. Number 25, if measure of angle L was 87 degrees and measure of angle Y was 94 degrees. Well, L doesn't correspond with Y, so you're thinking possibly. I'm thinking one step further, which is going to say probably not, though. And here's how I want to say it. And I need to make sure that this makes it, like, I'm already seeing how it would work. So I just need to figure out how to write it and explain it best to you guys. So this is not possible is what I'm going to say here. So no, this is not possible. I'm going to start with that. Although L and Y do not correspond, if the triangles were similar, then their corresponding parts would have to be congruent. But a triangle with measure of angle Y equal to 94 degrees means the other two angles would sum to 86 degrees. This is because 94 plus 86 is 180. And 87 is more than 86. So the third angle, or so angle L's corresponding part, JKL, Y, XYZ. So measure of angle Z would have to be less than, or it couldn't be, I should say, could not be 87 degrees. The best it could be is anything just less than 86 degrees. So I don't know if I explained that perfectly, but it's basically this. I'll kind of draw it out. It doesn't matter what they look like, so whatever. JKL, XYZ. So Y, if Y is 94 degrees and L is 87 degrees, you're saying, okay, if L is 87, then Z would have to be 87. That can't happen. 94 plus 87 is already 181 degrees. I think that's a better way to explain it. 94 plus 87 is already 181 degrees. Already more than 180. Forget X. This is already more than 180 right here. That's just not possible in that case. Or same thing here. 87, this couldn't be 94. Probably a better way to explain it in general. Number 26. Measure of angle J plus measure of angle K equals 85 degrees. And measure of angle Y plus measure of angle Z. What did I do? Equals 80 degrees. J and K, Y and Z. Well, Y would have to be the same as K based on this. So I'm going to look at what would happen with K. So measure of angle K would be 85 minus measure of angle J. And measure of angle Y would have to be 80 minus measure of angle Z. I'm probably not thinking about it the right way just yet. I want to see how this works if I just play with this a little bit more. Measure 85 minus measure of angle J equals 80 minus measure of angle Z. So I'm setting these equal. If K would have to equal Y and these two would have to equal each other. So what happens if I do something like add these to both sides or something like that, or subtract these from both sides? I really just want to play with having these on the same side of the equation or something. If I subtract 80 over, then I get 5. And if I say add the measure of angle J over, measure of angle J minus measure of angle Z would have to be 5. Does that do anything for me? J and Z? Difference between J. Okay, I don't know if I did anything that mattered. Let's just go back to the thought. If J and K equaled 85 when added together, Y and Z were 80 when added together, that would mean both. That would mean all sets of angles would be acute. Okay. I'm going to say this isn't possible. Sorry that I worked this. I don't think any of this mattered. I'm going to say this isn't possible. Here's where I'm going with this. K does correspond with Y. So these would have to be the same measure, whatever they are. Because they're adding with other angles and they're less than 90 degrees when adding those angles, then that means these angles themselves are less than 90 degrees. So these angles are acute. They're adding with another set of angles and maintaining that as well. So every angle that we're looking at is acute, which itself isn't a problem. But J doesn't correspond with Z. J corresponds with another angle, and that other angle would also therefore have to be acute. But these are showing that you'd have to make something obtuse. And I need a 95 degree angle here to complete 180. And here I need a 100 degree angle to complete 180. So I don't know how to explain that well. But this isn't possible. It's not that this isn't possible for, this is not possible for the triangles to be similar. Because I'll say this. Because both sets of triangles, would have to be obtuse, yet our knowledge of the angle measures provided shows all sets of angles which would correspond and be equal would have to be acute. It's one of those indirect proof kinds of things, like, oh, well, let's assume that they are similar. If they're similar, then these would have to all be acute, yet in these triangles, we'd have to have an obtuse angle, therefore it wouldn't really work out. That's where I'm drawing the connection. Yeah, it's hard for me to explain what I'm seeing in my head on some of those, and I should be better at it. It's what I get paid for as a teacher, not for you guys. It's what I get paid for as a teacher. Okay, number 27, mathematical connections. Explain how you can use similar triangles to show that any 2 points on a line can be used to find its slope? I'm wondering if they want to talk more on angle or if they want to talk more on proportionality. Explain how you can use similar triangles to show that any 2 points on a line can be used to find its slope. I mean, because you can reduce the fraction. I'm trying to think if they want to talk about angle, because generally we don't talk about angles when we're doing slopes of things. The ratios of these things will have to be equal. So yeah, you set up a proportion. I guess you don't have to reduce the fraction, but they're equal. When you create a slope, when triangles are similar, corresponding. Okay, so how about this? The vertical lines are going to be in proportion with the horizontal lines, right? Because the triangles are similar, I guess you can just say that they are. There's enough to do that. Because the triangles are similar, the ratios of the vertical line, well, I guess not lines, sides, the ratios of the vertical sides to the horizontal sides are equal. I guess that works out. Okay. All right. Yep, that works for me. Okay. Number 28. How do you see it? Let's get this ready. In the diagram, which triangles would you use to find the distance x between the shoreline and the buoy? Explain your reasoning. So I want to find x. Let's see. So clearly I want to use this triangle, LKM. And yeah, and I'll use this guy right here, this LJN. Wait, the distance from the what to the what? Oh, x. Oh wait, that doesn't correspond here. Oh, I know 100. Yeah. Okay. So I would use triangle. Okay. So I would use triangle LKM and triangle LJN. They are similar by angle because of the right angles and reflexive property. Right angles and reflexive property. Sorry for shorthand, even though I'm typing it. So they're similar by angle, and KM equals 100 because of the rectangle thing. Because opposite sides of rectangles are congruent. And x plus 20. Now, they didn't ask us to find this length, but I will find it for you. And x plus 20. LJ is x plus 20. And JN is 100 plus 25, which is 125. So we can set it up this way. We can say x, that's LK, over x plus 20, that is LJ, equals, that's the left side of the small to the left side of the big. Now let's go the bottom side of the small, KM, 100, over the bottom side of the big, 125. Before I cross multiply, 100 over 125 is 4/5. As I will now cross multiply, I get 5x equals 4 times x plus 20 in parentheses, or 5x equals 4x plus 80, or x equals 80 meters. They did not ask us to find it, but I did. Number 29. Explain why all equilateral triangles are similar. All equilateral triangles are similar because all equilateral triangles have 60-degree angles. All equilateral triangles are, is that equilateral? Equilateral triangles are similar because they all have only 60-degree angles. Ugh. 176 angles. This means that they will always satisfy the angle-angle similarity theorem. That's it. All right. Number 30. Thought-provoking. Decide whether each is a valid method of showing two quadrilaterals are similar. Justify your answer. So I kind of answered this earlier. It was one of the error analysis questions. Angle, angle, angle. See, well, they mentioned the angle, angle. They tried to use angle, angle. And I said that's not correct. Number one, that should work for triangles only because you only would need, because you don't really, because it only has 3 angles. But number two, triangles are very special in this way. Angle, 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 even though, and listen, part B is the same. If I know 3 angles of a quadrilateral or 3 sets of angles of 2 quadrilaterals are congruent, that means the fourths are automatically congruent. So whatever my answer is for A is going to be the exact answer for B. I'm going to let you know that right now. So A and B, I'm just going to tell you, are both no. Now, why? I can show you a counterexample. Let me show you 2 rectangles. We know that in 2 rectangles that all 4 sides or all 4 angles are congruent, right? All right angles. Are these similar? Are the sides proportional? No. Just because I know that this is congruent to this is congruent to this, and this is congruent to this, I should say. Congruent to that, congruent to that, and congruent to that. Well, you will find out that these are congruent and that they're right angles even. That doesn't mean that these 2 sets of things are proportional. Rectangles can be in any size that you want them to be. They could be a square-like thing. They could be really long. It doesn't just have to be rectangles, by the way. I can use parallelograms. I can use trapezoids. But this is just an exception to this kind of thing that neither is going to work in these cases here. And if angle, 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 angle is not going to work, then neither is angle, angle, angle. So triangles are very special for something like this. Now, if I found out that there was something else that was in proportion here to work something, then yeah, it's possible. But you'd have to get a lot more built out. And that's just not enough. Okay, number 31. Without using corresponding lengths in similar polygons, prove that the ratio of 2 corresponding angle bisectors in similar triangles is equal to the scale factor. But, okay, hold on. Let me draw... let me do like a right... angle bisectors. Okay, that's fine. Let me just do one of these and copy and paste it and make a bigger one. And trying to see what they're trying to say. So let's say that we had 2 similar triangles, and by and large these are similar just because of how I drew them. If I did an angle bisector, like, do I thin it out? What do I do? If I do an angle bisector like this, and by the way, I'm doing an angle bisector, not a segment bisector. Not a median. So I'm saying like that's congruent to that, and then I do another one here. Sure. Like that to that. Now they already said the triangles are similar, right? So that means these would have to be congruent to each other there, and this is congruent, and this is congruent like that. What do they want? That the angle bisectors in similar triangles is equal to the scale factor. Well, if the triangles are already similar, then they already possess some sort of scale factor. Let's call this length A and B. A and B. Well, here's what I'll say. If these 2 triangles are similar, then you have, the corresponding angles thing, right? That are congruent. So these are congruent to each other and all that. And when I make an angle bisector, then that means that these little parts are congruent as well. So now I've created another brand new set of similar triangles right here and right here, because you can see angle, angle marked, even the way that I made it. Sorry for the thick thing here. This is congruent to that. Remember, they're part of angle. An angle bisector divides both angles into 2 congruent parts, and those angles were already congruent. So these 2 are congruent. Those 2 are congruent. I have angle, angle for that. So this A to B, or B to A, if you want to call it an enlargement, scale factor is still going to be the same thing. It's going to have the same scale factor as anything else did here. So equal to scale factor, and because we have other parts here that would still share that same side length, for example, I should probably use, instead of using A and B, let's call this like triangle ABC and DEF or something like that, just to kind of get it a little better. And no, I'm not going to do a whole typing thing. I'll do parts of one, but not like a huge proof. Let's call this triangle ABC and triangle DEF and part G and H, right? So I'll say ABC. Remember, they tell us they're already similar. Triangle ABC is similar to triangle DEF. So parts that are congruent and all that. Now we find out the angle with the bisector, angle CAG is congruent to angle FDH, and angle C is congruent to angle F. So now we can say, because of these two things, kind of a flowchart thing, triangle CAG is similar to triangle FDH by angle. And we already know some parts here that make the scale factor, like AC to DF. So AC to DF is equal to this AG to DH, which should be the same as your K. Yeah, let me reverse how I say that, though, because the whole point is showing that AG to DH, the bisectors are. AG to DH is the same, AG to DH, and I know that this is more the reduction version, but that's okay. AG to DH is the same as CA to DF, both original parts, AC to DF, which is the same as the scale factor. So I guess that's enough. I hope that works out. All right, let's go to number 32. Prove that if the lengths of two sides of a triangle are A and B respectively, then the lengths of the corresponding altitudes to those sides are in the ratio B to A. Is there a way I can draw a scalene triangle? I want to do one that's, this might be one. It looks obtuse, but I can't tell if, okay, I can kind of scalene this out. I don't want it obtuse, though, actually, because then I don't want altitudes to go outside of this thing. Okay, I'm just going to make up a triangle thing that looks scalene enough. Let's do like that. That looks good. Okay, so I have a triangle, one triangle. The lengths of two sides of a triangle are A and B. A and B. Then the lengths of the corresponding altitudes to those sides are in the ratio B to A. So, because they're saying respectively, does that mean that if I do an altitude to A, this altitude to the other altitude has a ratio of B to A, even though it goes to A? Let me look into what they're saying. What kind of looks like an altitude here? Let me make B in green. Actually, let's do A in green. What's going to probably be more important is that I can make a triangle out of this here. So, okay. So check this out. Hold on. I don't know if this is a full answer. I'm just looking into. I'm asking myself what this has to do with triangle similarity when I don't see two triangles here, but now I actually see a sense of two triangles. So check this out. The reason I brought this one in blue, even though it goes down to A, is because over here in blue I can make B basically the hypotenuse of this right triangle. Remember, this is an altitude. And then A is going to be a part of this green triangle here, so much so it's going to be the altitude, the hypotenuse of this green triangle, which has an altitude that's over there. So notice those two triangles. They do have congruent angles there, and they share an angle right here, which is congruent to itself. Therefore, we do have two similar triangles by angle. Now, I'm not writing out, I probably should, I'm not writing out what all these letters are, like A, B, C, D, E, F. but let's just give them a little x to y thing. Like x is the whole thing, okay? X is the whole thing, and y is this whole thing right here. If that makes sense. All of x, all of y. In the blue, oh shoot, let's give them those colors. X is going to be the blue, y is going to be the green. Okay. What did they say here? If the lengths of two sides of a triangle are A and B, then this altitude to this altitude is B over A. That makes sense because X is in the blue triangle. So these two triangles are similar. Therefore, corresponding sides are proportional. So X is to Y just as in this triangle B is to in that triangle A. Yes, that does make sense. Yes, that checks out. Because X is part of B's triangle that's similar to Y and A's triangle and all that kind of stuff. So, yes. I didn't really explain it. I didn't write out the explanation, but I think that works. All right, and lastly, number 33. How much time have we done so far? An hour 15 or so. Lastly, problem number 33. Modeling with mathematics. A portion of an amusement park ride is shown. Find the length of EF, justify your answer. Let me copy paste this over. Okay. Is that like a roller coaster? Oh, I see. Okay. EF is right here, and we have lengths 40 and 30. So if I have like a right triangle there, then that would be similar to it, but I don't have any other lengths of that, so that doesn't help me. But this would be similar. Oh, but I don't know that that one's similar to that one. There's nothing that tells me that. These share a side by reflexive property. Those wouldn't be similar, actually. That wouldn't work. Well, these are right angles. These are right angles, so these are parallel lines with the ground. If these are parallel lines, then we do have like alternate interior angles here and here, and alternate there and there, or vertical angles here and here. So I could do something like AD is parallel to BC by the perpendicular line stuff. I'm not going to go over a bunch of reasons, but same side interior angles are supplementary, or two lines perpendicular to the same line are parallel to each other, stuff like that. So that's that. Therefore, angle DAE is congruent to angle BCE by angle. Not by angle. Alternate interior angles. And AIA. And then also the angle E vertical angles. Angle AED is congruent to angle CEB. Vertical angles. I don't know if it says explain. It says say justify. So triangle AED is similar to triangle CEB by angle. Okay. If they're similar, then 40 is to 30. Let's see. 40 is to 30 as... What does that have to do with EF, actually? I just assume it has to do with triangle similarity, and other ones aren't similar because of that. EF. Let's see. What can I say about EF here? How about this? Let's see. How do I say this? How about this? Now that I know that 40, not 40 is 30 as whatever, but 40 over 30 is 4/3, right? That means that, and I don't know what these lengths are here, but if this was 4, then this would be 3 right here, basically, is the way that I want to say it. If this was 4, then this would be 3. It has a 4-to-3 ratio. That means that this has a 4-to-7 ratio right here. Okay? The reason I bring that up is because EF is now in this triangle, which is similar to this triangle, for example, right here. They are similar for that same kind of thing for a different reason, but that's a 4-to-7 ratio, or 7:4 and all that kind of stuff. So 4:7 as EF is to 30. That would work out. So knowing I had similar triangles before, here's another set of similar triangles I can work that out with. I don't know if that kind of makes sense, but 3 plus 4 is 7 is what I'm saying there. So I could use that. So if I multiply both sides by 30, then I get EF is 4 times 30 over 7, or 120 over 7 feet. I don't think 120 divides by 7, so I'm going to leave it like that. Or I say it's about, I don't know what it's about. I'm sure an exact answer is probably best for something regarding similarity. Otherwise, that wouldn't work out. So that would be that final answer there. Again, what I did was I determined these two triangles were similar here, boom and boom. And then I used corresponding parts that should be proportional, and I built a new proportionality out of it for these two triangles here, which are also similar to each other, also by angle. It's just sets of parallel lines and things like that, and perpendicular and all, or reflexive property, this and that. All the stuff would have worked out in its own way. And then I used that proportionality against the 30 to get that one there. So it seems to work. All right, guys, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I know I stumbled along problems in some different ways. That's like, I don't know if this is best to say. I don't know how to best say it to you. But I think I achieved what I needed to with it. And that's what I love about sight reading these problems, is in full transparency, having the same kind of discussion through these problems, the way that my brain would work through them. If I did them myself, I would have faster means of going about it. But as I'm talking with you guys, I don't know what I'm seeing in the background. As I'm talking with you guys about it, I want to try and find ways to say how I can best explain it to you and have you have that same thought. So I hope that worked out. Coming up next should be an 8.1 to 8.4 solution quiz solution guide video, because I think that's what comes up next in the book. So be prepared for that. Later on, we hit sections 8.5 and 8.6, and I'm going to obviously do all the reviews within the textbook itself. And you'll probably also see one of those "Are you ready?" things that we started to do in our school as well. All right, guys, thank you so much. Take care, and I will see you in the next one.